A cheap car cannot be cheap where it matters most, your safety. Self-driving can fail because of sunlight, not because the AI isn't smart enough. And batteries don't listen to marketing promises. Batteries listen to physics. I'm going to answer 5 questions today that Tesla hopes you won't ask. Can a budget-friendly electric vehicle survive a real crash without becoming a total loss nightmare? Will those fancy Cybercab-style doors trap you next to another car or make it impossible for someone with a bad back to get in and out? How will Tesla maintain crash safety when building millions of these cars faster than ever? Does that 8 gigawatt-hour battery expansion in Berlin actually mean anything for the price you'll pay? And where is full self-driving version 14 really at? And what will Model 2 inherit from all that testing? I'm going to talk like an engineer, but I promise you'll understand every word. Setting the stage. What is Model 2 and why the confusion? Tesla has never officially confirmed the name Model 2. What the market is talking about is an entry-level vehicle with a target price of $25,749. The Cybercab is Tesla's concept for a dedicated robotaxi, pulling their entire production strategy and self-driving development along with it. You've seen conflicting images floating around: 2 doors, 4 doors, hatchback designs. Here's the reality. Different concepts are being tested simultaneously. Different test mules are running around Giga Texas and California roads. Different artists and YouTube channels are creating render predictions based on limited patent filings and blurry spy photos. Some of what you're seeing is real. Some is educated guessing, and some is completely fabricated by AI image generators hoping to get clicks. The confusion isn't accidental. Tesla deliberately keeps details vague during development to maintain competitive advantage. They learned this strategy after competitors copied design elements from Model 3 before it even launched. But this secrecy creates a problem for you as a potential buyer. How do you separate fact from fiction when making a $25,000 decision? Here's my approach. Instead of arguing about which rendering looks most accurate or debating whether leaked photos are legitimate, let's focus on 3 fundamental things that will determine if this vehicle is real and worth your money at $25,749. The battery technology and supply chain, the production capability and manufacturing strategy, and the autonomous driving technology that's actually shipping in these vehicles. These 3 pillars will tell us everything we need to know about whether Model 2 can deliver on its promises. The 3 questions real buyers actually care about. Before we dive into technical details and manufacturing specs, let me ask you 3 questions that matter more than any promotional video or press release. First question, and this is critical for anyone over 55. Can you actually get in and out of this car without help? I'm not talking about a 25-year-old with perfect flexibility. I'm talking about you. If you use a cane for stability, if your back isn't what it used to be and bending causes pain, if your knees complain every morning when you stand up, can you slide into this vehicle without struggling? Door geometry, seat height relative to your hip level, the turning and twisting motion your body has to make, these aren't minor comfort details. For many older drivers, these factors are absolute deal breakers that determine whether a car is usable at all. Second question, and this one hits your wallet directly. If someone bumps into you in a parking lot, does that small dent turn into a financial disaster? This is the question that keeps insurance companies up at night and should concern you even more. We're talking about repairability in the real world, insurance rates that compound over time, the total loss threshold where your insurance company runs the numbers and decides it's actually cheaper to write off your entire car than repair the damage. A vehicle priced at $12,749 can cross that line frighteningly fast with damage that looks minor to your eye.
third question, and this one's about your physical safety on the road. Is a small, lightweight car actually safe when you're driving next to Ford F-150s and Chevy Suburbans that weigh twice as much as you do? We need to talk about structural integrity that protects the cabin during impact, crumple zones engineered to absorb energy properly, cabin protection that keeps you safe when physics says the bigger vehicle has the advantage. If Tesla can't answer these three questions convincingly with real data, not marketing promises, then everything else they're talking about is just noise and speculation.
The door reality. Beautiful doesn't mean functional. Let's talk about those doors everyone's excited about, because there's a big difference between a door that looks impressive and a door that works in the real world. There are two concepts people constantly confuse. Side clearance is how much space the door needs when fully open. Swing path is the arc the door travels through. You can have a design that looks like it opens wide, but if that swing path extends into the neighboring space, you've got a problem in crowded parking lots. Engineers have ways to reduce this risk. Multi-axis hinges that change the door's trajectory. Sensors that limit how far the door opens based on detected obstacles. Two-stage opening systems, where the door cracks open just enough to check clearance before swinging wide. But here's what matters more for someone over 65, accessibility. The ideal seat height allows you to stand next to the car, rotate your body, sit down, then rotate your legs inside. No bending, no twisting your spine, no dropping down into a low seat or hauling yourself up. If Tesla is serious about building a car for older drivers, this is where the engineering must focus. A door that goes viral on social media is worthless if it causes you back pain every time you use it.
Repairability and the total loss trap. This is where we need honest conversation about what happens after an accident. Why do affordable cars become total losses so quickly? Insurance companies calculate total loss based on labor hours required, wait time for parts, whether the frame is damaged, and the safety risk of driving a repaired vehicle. For a car priced at $12,749, you can hit that threshold with surprisingly minor damage. Designing for repairability is completely different from designing for manufacturing efficiency. A successful mass-market vehicle needs panels and parts that can be replaced individually, a structure that can be realigned without specialized equipment, standardized components, and repair procedures that work at independent shops, not just Tesla service centers. Those special doors, they're expensive to repair because of hinge mechanisms, sensors and actuators, and complex alignment procedures. If Tesla wants Model 2 to be a true mass-market vehicle, they need to prove one thing: a minor fender bender won't generate a $10,000 repair bill. Think about it. You're on a fixed income. Social Security provides your monthly budget. You get rear-ended at a stoplight, nothing major. But because of how the car is designed, that impact damages structural components that can't be repaired, only replaced. Suddenly, your car is declared a total loss. Your insurance pays the depreciated value, which might be several thousand less than what you still owe. This scenario isn't hypothetical. It's happening right now with several electric vehicles.
Safety and structural integrity, surviving in a world of bigger vehicles. How does a small, lightweight electric car protect you when surrounded by 3-ton pickup trucks and massive SUVs? 3 engineering factors determine crash safety. First, crumple zones that absorb impact energy by deforming in a controlled way. Second, load paths that direct forces around the passenger cabin rather than through it. Third, cabin integrity, a protective cage that maintains its shape even under extreme stress. Here's something that surprises people. A stiffer car isn't always safer. You need the right balance of energy absorption and structural rigidity in the right places. Tesla can't simply copy crash performance from Model 3 or Model Y into a smaller vehicle. The physics don't work that way. However, they can leverage their design philosophy and simulation experience. Tesla has run thousands of virtual crash tests. They understand how to optimize structures for multiple impact scenarios. That knowledge transfers. But here's what you need to remember. Until we see actual crash test data from the National Highway Traffic Safety Administration and the Insurance Institute for Highway Safety, everything else is speculation. Those ratings are the only objective measure we have. Marketing videos don't protect you. Engineering simulations don't protect you. Independently verified crash test results protect you.
Berlin battery expansion, the key to real affordability. Now let's talk about something that sounds boring, but actually determines whether this vehicle can be affordable: the battery production expansion at Giga Berlin. Tesla has confirmed a major investment, close to 100 million euros for battery manufacturing, with a goal to reach 8 gigawatt-hours of annual output by 2027. That's part of a broader investment, bringing Tesla's total commitment to local battery production in Berlin close to 1 billion euros. Andre Turing, Tesla's senior manufacturing director at Berlin, called this a decisive step toward full vertical integration. Here's why this matters. Right now, Giga Berlin assembles Model Y vehicles, but imports battery cells primarily from China and the United States. That exposes Tesla to shipping costs, geopolitical tensions, and supply chain disruptions. By manufacturing cells directly at Berlin, Tesla gains tighter control and reduces transportation complexity. But Tesla also admitted something important to Reuters. They stated that producing batteries economically in Europe is currently almost impossible, given intense international competition from China and the United States. Let me explain from an engineering perspective. Batteries typically account for 30 to 40% of an electric vehicle's cost. If you want an affordable EV, you must optimize both the battery technology and the supply chain. Vertical integration helps reduce costs, but it can't change the fundamental physics of battery cells. The improvements we should expect are incremental, step-by-step advances, not revolutionary breakthroughs. And here's the competitive reality. 250 to 300 miles of range? Many manufacturers achieve that. Tesla needs to win on different factors: efficiency measured in miles per kilowatt hour, software optimization, and total cost of ownership, including insurance, repairs, and maintenance.
Charging, don't overlook level 2. While everyone focuses on fast charging stations, let me tell you what actually matters. Level 2 charging at home. Charging overnight at home using a level 2 charger is the cheapest and most convenient way to keep an electric vehicle powered. You plug in when you get home, and the car is fully charged by morning. Fast charging is primarily for long road trips. For regular daily driving, grocery stores, visiting family, appointments, home charging makes electric vehicle ownership practical. If Tesla wants Model 2 to serve older drivers effectively, they need to prioritize 3 things: seamless home charging experience, real-world range that covers typical daily needs with margin to spare, and simple charging guidance that doesn't require technical expertise. An affordable car doesn't give companies permission to deliver an inferior experience. If anything, the experience needs to be even better because you're asking people to trust new technology while spending carefully saved money.
Real-world range. The truth about small battery packs.
Let's talk honestly about range, because this is where EPA estimates and real-world experience diverge dramatically. If Model 2 uses a battery pack around 50 kilowatt-hours, the official range estimate might look acceptable under ideal conditions. But consider what happens in reality. You're driving 75 to 80 miles per hour on the highway. You're climbing elevation through hilly terrain. The temperature is below 40 degrees and you need the heater. You're carrying passengers and luggage. Every factor reduces your effective range, and they compound each other. Tesla can win this challenge through superior engineering, better thermal management that maintains battery efficiency in cold weather, more efficient motor and inverter systems, aerodynamic design that reduces drag at highway speeds, and sophisticated software algorithms that optimize energy consumption. For a vehicle with a modest battery pack, these optimizations are the difference between a car that meets your needs and one that leaves you anxious about running out of charge.
Austin ROBOTAXI testing. What the viral videos actually prove. You've probably seen the videos. Elon Musk and Tesla's AI director sharing their experiences riding in fully driverless vehicles around Austin on Christmas Eve. Musk described it as perfect driving. The AI director posted video from the back seat with both front seats completely empty. These aren't simulations. These are real vehicles operating on public streets in real traffic. But here's what's actually valuable about these tests. Every mile driven without a safety supervisor generates data, edge cases, unusual traffic patterns, unexpected pedestrian behavior, construction zones, emergency vehicles. This data feeds directly into improving full self-driving performance. More importantly, for Model 2 buyers, it refines braking algorithms, traction control systems, and energy management strategies. The autonomous driving system that eventually ships in Model 2 won't be a first-generation experiment. It will be technology that's been tested under the most demanding real-world conditions. Think about that. The self-driving capability you might use isn't being developed in a laboratory. It's being refined through millions of miles of actual driving in cities like Austin and San Francisco.
Camera glare, when physics defeats artificial intelligence. Here's a problem that sounds trivial but could derail autonomous driving. Sunlight. Tesla's full self-driving system relies on cameras to see the world. When direct sunlight hits those cameras at certain angles, it creates glare that degrades image quality. Even human drivers deal with this, using sun visors and sunglasses, but an autonomous system can't squint or turn its head. Tesla has filed a patent for an anti-glare panel using microscopic cone structures to scatter incoming light in multiple directions, reducing glare while improving camera perception. These microcones are precisely engineered for size, angle, and orientation. Additionally, a mechatronic system can dynamically adjust their positioning based on the sun's location. This is what I mean when I say batteries listen to physics, not marketing. The most sophisticated AI is useless if the cameras can't see clearly. Tesla is also exploring other solutions, including direct photon counting technology and neutral density filters in future hardware versions. A reliable self-driving system is one that sees clearly in the worst conditions. If you're 65 or 75 and counting on autonomous features to compensate for reduced reaction time or vision limitations, this engineering detail matters enormously. Cybercab test mules, why they have mirrors. A Tesla Cybercab has been spotted in downtown Austin traffic with small side mirrors and possibly a temporary steering wheel. Some viewers assumed this contradicted Tesla's vision of a fully autonomous vehicle without manual controls. Let me explain what's actually happening. Current federal motor vehicle safety standards require mirrors and manual controls for vehicles on public roads. Tesla is working toward a dedicated regulatory framework for autonomous taxis, but until those rules change, test vehicles must comply. This isn't a design failure, this is compliance engineering. Tesla follows a consistent strategy: adapt the hardware just enough to meet today's legal requirements while collecting data needed to eliminate those components tomorrow. The goal is validating safety, redundancy, and system behavior under real urban stress before mass production begins. For Model 2, this matters because Cybercab is Tesla's most aggressive test bed for autonomy-first design, cost reduction, and regulatory navigation. The lessons learned from deploying a purpose-built autonomous vehicle at scale feed directly into Tesla's broader next-generation platform. FSD version 14 and the physical Turing test. NVIDIA's robotics chief, Jim Fan, recently called Tesla's full self-driving version 14 the first AI to pass what he terms the physical Turing test. This benchmark measures whether AI can demonstrate human-like intelligence through physical actions, specifically how convincingly it handles real-world driving. Fan, who leads NVIDIA's project GROOT, tested FSD version 14 in his own Tesla. His assessment? Initially, the experience felt extraordinary, almost magical. Over time, using the system became intuitively natural, like using a smartphone. Removing it would now feel disruptive. Elon Musk noted that version 14 allows users to feel the maturity of its awareness, calling it the best practical AI available today. But let me separate two different things. The fact that autonomous driving technology is advancing rapidly is legitimate and exciting. However, that doesn't automatically mean the vehicle carrying that technology is safe in a crash or affordable to repair. These are separate engineering challenges. Model 2's success depends on solving both.
Let me give you 5 clear conclusions based on everything we've covered. 3 things you can reasonably believe. The Berlin battery expansion is a real prerequisite for making Model 2 affordable in Europe. The ROBOTAXI and Cybercab programs are genuinely generating data needed to mature full self-driving quickly. And Tesla is solving fundamental physics problems like camera glare, not just relying on better AI. 2 things you should watch carefully before spending your money: actual crash test ratings and structural safety data from independent testing organizations, and the real-world economics of repairability, including insurance costs and total loss thresholds. Now, I want to hear from you. If you had to choose, what should Tesla prioritize for Model 2? Would you rather have a car that's inexpensive to repair with low insurance costs, or would you prefer the most advanced self-driving technology available, even if it costs more to maintain? Leave your answer in the comments. Option A for low repair costs, or Option B for cutting-edge autonomy. If you found this analysis valuable, hit that subscribe button right now. Click the bell icon so you don't miss our next video, where we'll examine whether the Tesla Pi phone rumors have any basis in reality. Share this video with anyone considering an electric vehicle, especially if they're concerned about safety, repair costs, or whether these cars work for older drivers. I'll see you in the next one.